Okay, so the next talk is by Professor Peeter Saari. He is a notable physicist, and from my opinion, he represents optics in Estonia. He has made notable contributions to the development of, say, several optical concepts. And his talk is on optics in Estonia, research and innovation highlights. As many of us may not be aware of, Estonia has a very rich history in optics. Several Estonian researchers have made notable contributions to the field of optics. So let us welcome our speaker, Professor Peeter Saari.
Now it's okay?
Yes.
Nothing. Do you see?
Yes, yeah.
Oh, right. First of all, I would like to thank the conference organizers for inviting me to give the opening lecture. So let me move on. I don't, again, a problem. As you know, many things in the history of optics have been named after the scientist or inventor. If we now ask whether any of Estonians, of whom there are only 1.3 million, have left their name in the history of optics, the answer is yes. This is Bernard Smith, inventor of Smith camera. He was born in a small island, Naissaar, near the capital of Estonia, Tallinn. We are here in Tartu, by the way. And while in Germany, before the World War II, he continued his activity in inventing every kind of machines, and he, by the way, built the telescopes also. And he managed to figure out what should be the correction plate for telescope in order to eliminate aberrations, spherical, coma, and to make the images of stars unprecedentedly sharp and good. So his invention, by the way, he made this plate by his own single hand, because he lost his second hand in an accident where experimenting with his other invention on the island, Naissaar. And this plate was so successful that several observatories have invented. By the way, do you see the whole screen, or maybe my? Okay, let me switch the screen off. No. Okay. So his plate was very successful, but this was before the war. Now, actually, academic optical research in Estonia did not emerge until the 1950s, when luminescence studies began in Tartu. And mainstream of Tartu physics is material science, solid state physics, but still optics is has been also present. So I had a very serious problem what to select out from achievements of Estonian optics. And the selection criteria I chose was the following. First of all, work done in Estonia. Then the achievement has to be important in a worldwide science. And the criteria is that the pioneering paper has to be cited at least 50 times. Actually, we have works with citation more than 500 times, according to Web of Science and for Global Scholar. And if there is a monograph devoted to the emerged research field, also I indicated this. And so, according to these criteria, I quoted 7 highlights, but today I am talking about only 2 or 3 of them. Discovery of the phenomenon of persistent spectral film. And since our conference is devoted to holography, I would like to tell you about the main idea of time-space holography, which was by love in 1980s. And finally, I'll speak about photoelasticity methods, because by this method recently a very intriguing mystery of Prince Rupert's chairs was solved. So let's start about persistent spectral hole burning. If certain frozen solution or certain time molecules have an absorption spectrum which is inhomogeneously predominant, then it turns out that under the illumination by monochromatic laser light, some molecules, due to the photochemical or photophysical processes, bleach out, and as a result, a hole occurs in the absorption spectrum. And actually, such a material is photosensitive material, which has very high resolution sensitivity to colors, to the frequency of light. And this enabled us to invent time domain holography. Let me remind you the basic principle of holography. As you know, because photomaterial is a quadratic detector, when we record the light wave, we lose the phase of the wave, and only amplitude squared is recorded. And the principle of holography is that if we add a reference wave, then this wave will interfere with the signal wave, and the recorded total light will contain information about phase. This is a reference light, and this is signal light. Now, the idea of time domain holography is very simple. If we now replace the one spatial coordinate x by the frequency, and as I told you, spectral full burning enables to record spectrum, then we get the possibility to record the information about spectral phase as well as about the spectral amplitude. And in every spatial point. And instead of inclination angle in the reference beam, now the reference is a pulse, delayed pulse, and instead of inclination, here the constant will be the delay of the reference pulse. Now, this is inhomogeneously broadened absorption spectrum. This is now object spectral amplitude, which is a modulus squared of the Fourier transform of the temporal behavior of the signal. And if it's interfering with reference pulse, we can record this spectrum as spectral holes in the plate made from the spectral full burning material. And the recording process is as follows. This is plate. This is first is a reference pulse falling to the plate, and then time-dependent and space-dependent signal. Now, in this case, we have 1, 2, 3, 4 pulses. Every of them have different spatial cross-sectional structure. And playback after, say, 20 minutes or 1 hour or next day, it depends how long you can keep the plate at liquid helium temperature, which is 4.2 Kelvin only. And if you illuminate this plate by readout pulse, then after the pulse, the signal will be played back. And it's important that independence of whether the readout, whether the reference pulse was the first or not, the signal will be played back in normal temporal ordering or in reverse temporal ordering. And also, if they overlap in the process of recording, you can split the playback into 2 parts. And this is a picture taken from the hologram, which shows the quality. Of course, in this case, we see only the spatial resolution, the spatial quality, but you have to imagine that these images are flying out from the cryostat, from the plate, with frequency 82 megahertz. So a lot of money can be collected, but this is holographic money, and unfortunately, this is money of the Soviet Union, so it doesn't have any value anymore. Now the second part, I just mention you that the information about our companies, about 10 of them, you can read in the paper I sent 2 days ago. And start the building, designing, and construction and production of optical equipment started in 1960s, and you see our equipment had been used in Soviet space program. And what is interesting that this design of optical equipment started for the space and for the Soviet space program, and now another young company is working also on optics for space programs, and in this case for NASA and for the European Space Agency. And finally, about this achievement in basic science, development of experimental and theoretical methods of photoelectricity, which started in 1966 in Tallinn Technical University. And these are the pioneering papers and books. And the very interesting and very recent results of the company which they have founding company Stress in cooperation with Purdue University. They solved the 400 years old mystery of Prince Rupert drops. These are glass drops, and I just want to show you the video about these drops. Do you see the screen? Do you see?
Yes. Yeah.
So the mystery is, yes, that the head of the trap is very strong, but the reason is that the drop has very special distribution of residual stresses, and the picture, the distribution of these stresses has been computed from the polariscope picture, and so the mystery has been solved. And that's all I wanted to say, and I wish you a successful conference. Thank you.
Yeah, thank you very much, Professor Peeter Saari, for the wonderful talk of a historical glimpse of all the contributions from Estonian researchers. So thank you very much. And so now let us ask the audience, if you have any questions, so you can raise your hand and you can directly ask the speaker. Alternatively, you can also post your question in the chat window, which we can directly ask the speaker. Okay, so I have a question, Professor Peter. So so you have already made a notable contribution to this space-time holography. So what do you think is the future of holography in terms of space-time concepts?
You mean this version of space-time holography, or?
Yes.
No. Future is not great because it's very impractical, because it needs keeping of the holograms in liquid helium temperature. This is, by the way, reason why spectral memories, which are based on spectral flow burning, and which were studied very intensively in IBM, by the way, and by Werner, Nobel Prize winner. Simply, flash memories turned out to be such good things, with such a high density of capacity of the memory, that nowadays no need for optical memories. Maybe only some very special applications, and that's it. No, of course, the principle of time-based holography can be realized also by other means, by spectral equipment, by the way, but then we lose the possibility of record the two dimensions of spatial dimensions. So unfortunately, this holography was a nice thing in the end of last century, but I cannot. As to myself, I'm working now completely in other fields of physical optics.
Okay, yes, yeah. Thank you so much, Professor Peter.